Okay, test, test, test. Alright, AP Chemistry, this is Lesson 6 on periodic trends. We'll study further the periodic table and some of the properties of it. So previously we said that similar charges repel and different charges attract each other. These are referred to as Coulomb forces. So we talked about the fact that pretty much everything in chemistry revolves around this concept that positive attracts negative, negative repels negative, positive repels positive, and that's expressed in this formula, Coulombs Law, which states that the force between two electrical charges is equal to a constant called Coulomb's constant times the two charges, the charge on the first particle, the charge on the second particle. Could be two electrons, could be a proton and an electron, and then you divide that by the distance squared. So the farther apart they are, the less force that they exert on each other. And you may remember a formula from physics that looks similar to this. Gravitational force equals the gravitational constant times the mass of the first object, mass of the second object, divided by the distance between them. So it's not just a coincidence that the two formulas look almost identical, that it's because forces just behave the same way, no matter what kind of forces they are. So Fe is the force between the two charges. Q1 and Q2 is the magnitude of the two charges. In other words, how much they are charged, and d is the distance between them, and then you have to square that. The Coulomb's constant is 8.99 times 10 to the 9th power, and it's Newton's meter squared over Coulomb squared. You don't have to memorize any of this. I'm only going to give you one of these or two of these problems to do, just so you understand the concept of how you put a number value to this force between two electrical charges. So almost everything that happens in chemistry is the result of Coulomb forces. Okay, so let's look at an example. What is the Coulombic attraction between a proton, and there's the charge on a proton, we mentioned that number in an earlier lesson, and an electron has the same exact charge as a proton, just in the opposite direction, a negative, and they're separated by 0.7 nanometers. So this will be an example of how you're going to use scientific notation in problems, and a little illustration of how to deal with scientific notation. It looks a little scary at first, it just takes some practice. So there is the formula, the Coulombs Law formula, and there are the numbers plugged in. So let's take a look at them. On the left is Coulomb's constant, that's the K, and the units are Newton meter squared over Coulomb squared. And then on the top are the two charges, Q1 and Q2, and they're both exactly the same except one of them is negative. And on the bottom is the distance. So let's look at the distance. The distance is 0.7 nanometers. Nano means 10 to the negative 9th. That was a table that you had on a previous slide, and which I will provide for you shortly, as soon as I can get in touch with you. So it's it's 0.71 times 10 to the negative 9th meters, and then you square that. You square the distance. So let's look at how the units would cancel here. You have on the top coulombs times coulombs, that would be Coulomb squared, and that cancels with the Coulomb squared in the Coulomb's constant formula. And then on the bottom you have meters, and that gets squared, so that's meter squared, and that cancels with the meter squared on the top of the Coulomb's constant. So meter squared and Coulomb squared are gone. The only thing you have left is N, which is Newtons, and that is the measure of force. So that's how this constant makes the units cancel out appropriately so that you end up with the correct answer. Okay, so this is a big mess. How do you deal with all these numbers? Well, very simply, you multiply everything on the top and you divide by everything on the bottom. So let's do the coefficients first. And remember, the Coulomb constant, it only has one level, so it's considered to be on the top. So the coefficients, you would take 8.99 times 1.602 times negative 1.602, and then you divide that by what's on the bottom, which is 0.71, but it's 0.71 squared. One way you can do that is just divide by 0.71 and divide by 0.71 again. Don't multiply them, but divide by 0.71, divide by 0.71 again, or you can do what I did here and square it. And what you get then is 45.7686. Again, that's more significant figures than we're going to really want in this problem, but that's what we'll start with. Now, what do you do with the exponents? You add the ones on the top and you subtract the ones on the bottom. So on the top you have 9 plus negative 19, that's a minus 19, minus 19 again. And then on the bottom, here's what happens. You have that negative 9 and you square it. So that means it's going to be negative 9 times 2, because they're exponents. That was one of the principles of exponents we talked about in an earlier lesson. So you're going to end up with negative 18 on the bottom. But what that ends up doing is it ends up getting added to the top. In other words, negative 18 on the bottom becomes positive 18 up on the top when you add it in with the other coefficients. So what you have in all is 9 minus 19 minus 19 plus 18. So again, think about that bottom one. That's the one that's a little tricky and confusing maybe. And when you add those up, you get negative 11. So now with the coefficient, we're limited to two significant figures because of the 0.71. So that 45.7686, we're going to round to 46. That's the two significant figures. And the exponent is 10 to the negative 11. Then you adjust the decimal in 46 to make it 4.6. So you made the coefficient smaller, 46 to 4.6, so you have to make the exponent bigger. Negative 11 to negative 10. You go in the positive direction to make that bigger. And so your answer is 4.6 times 10 to the negative 10th coulombs. Very, very small amount of force between those two. We're just talking about one proton, one electron. Okay, Z number. Lithium has an atomic number of 3. The atomic number, as we talked about earlier, is called the Z number. The atomic number is the number of protons in the atom of an element. So there is a lithium atom, and it has 3 protons. Its Z number is 3. Core electrons. The core electrons are the electrons inside the valence orbital. So you generally have two types of electrons. The valence electrons, the one in the outer orbital, and the core electrons are all the electrons that are inside of the valence orbital. The core electrons are said to screen or shield the valence electrons from the pull of the protons in the nucleus. In the case of lithium, it's just one valence electron, but it could be more. So core electrons are all electrons inside of the valence orbital. These electrons screen the valence electron from the pull of the protons. So those two are core electrons. The valence electrons are the electrons in the outer orbital, and there it is right there. So you can see how I've drawn it in such a way that it kind of makes it obvious. Of course, these electrons are flying all over the place, but I've drawn it so you can see how the two electrons, the two core electrons, are standing in between the protons that are pulling in all of the electrons and that outer electron, that one in the valence electron. So how do you affect for that fact that the two core electrons are shielding, that is kind of blocking out the pull of the protons on that outer valence electron? And it's actually a very simple formula. So the effective Z number, and it's expressed as Z effective, measures how much of the pull of the protons each electron feels. So the Z effective is simply the Z number minus the number of core electrons. So in this example, lithium has an effective Z number of 3. That's the Z number for lithium, 3. It's how many protons it has, minus the number of core electrons. Those are the electrons that are blocking the pull of the protons on that valence electron. So it's simply 3 minus 2. It sounds like a real simple formula. It is. So what that means is, although lithium has 3 protons, its valence electron feels the effective pull of only one of the protons. So right there, that's basically what that outside electron is feeling. If you got rid of the core electrons, it's feeling just the pull of one proton. Therefore, it's not held nearly as tightly to the atom as you might think, because it is being shielded or screened. And shielding and screening are the same thing. Okay, the concepts we're dealing with today are really important. These are vocabulary terms that you need to become really familiar with. Ionization energy is one you're going to hear almost every day in the class. So ionization energy is the amount of energy that's required to pull an electron away from its atom. So the man represents ionization energy. The ionization energy must have greater pull on the electron than the protons do. If that little man can pull on that electron with more force than those 3 protons are pulling on it with, and remember there's a Z effective there for lithium of only 1 proton, then it'll be able to liberate or extract or pull out that electron, that valence electron, just like that. So ionization energy is also called electron binding energy. We almost never call it that. It's called that when you're dealing with a metal, but it's called ionization energy when you're dealing with a gas. And generally we're going to be calling it ionization energy. Okay, so ionization energies increase to the right. So the elements on the right side of the periodic table have higher ionization energies than the ones on the left. And it also increases as you go up. So what that means is the elements in the upper right-hand corner of the periodic table, that would be helium, neon, fluorine, chlorine, oxygen, those over there, have the highest ionization energies. So again, think of what that means. It means that it's really hard to pull their electrons away from them. High ionization energy means it takes a lot of energy to take an electron away from those elements. So ionization energies increase up a group, meaning going from bottom to top of the periodic table, and to the right in a period, so going from left to right. So the lowest ionization energies, consequently, would be the ones in the lower left. That would be rubidium, strontium, cesium, barium, things way down that you see way down there in the lower left corner. Ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. So you can see this is kind of a perspective view of it. It's not every element on the periodic table, but it gives you a sense of where the ionization energies are the highest. You notice a little bit of anomaly is hydrogen. That's because hydrogen is really not a metal and it doesn't have any core electrons to shield its electron. So it has a little bit higher ionization energy than the other elements over on that side of the periodic table. But the highest is clearly helium in the upper right-hand corner of the periodic table. So lowest ionization energies, highest ionization energies. Okay, so let's look at why the ionization energies are the highest in the upper right-hand corner. So in this just little segment of the periodic table, that would be where fluorine is. Fluorine has a higher ionization energy than lithium. It also has a higher ionization energy than bromine. So let's look at why that is. Ionization energies are lowest when an electron is furthest away from the nucleus, has more orbitals, and 2, the nucleus has fewer protons. So let's look at the first of this number 2 first. Lithium, over there on the left, has a lower ionization energy for its electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's, but it has only 3 protons to attract it, while fluorine has 9 to attract its electrons. So in other words, both lithium and fluorine are in the second row, second period, so they have the same, so they have 2 orbitals. They both have 2 orbitals. And while fluorine has more electrons, those second orbital electrons don't shield each other. You can think of them as being side by side to each other. So therefore, fluorine has 9 protons, whereas lithium only has 3 to pull its second orbital electron in. So because fluorine has more protons, positive charges pulling in on the electrons, it's able to hold on to them better than lithium is able to hold on to that 1 second orbital electron it has. Again, because fluorine has more protons and all of its valence electrons are all the same distance away as fluorine's valence electron, then fluorine is able to hold on to its tighter. That means it has a higher ionization energy, and it takes more energy to pull the electrons away from fluorine. Whereas lithium has a low ionization energy, and therefore it's easier to pull its 1 second orbital electron away from it. So there's lithium, there's fluorine. Okay, so let's look at bromine. Let's look at the difference between fluorine and bromine. So bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So its valence electrons are farther from the nucleus. This one's a little bit easier to understand. Now bromine does have a lot more protons than fluorine, but if you look at it, it has a lot of core electrons that are shielding those outside valence electrons from the nucleus. They're blocking the charge of the nucleus from pulling in those valence electrons. So its electrons are farther and farther away. Its valence electrons are much farther away from the nucleus than fluorine. And they have more energy because they're way out in the 4th orbital, because bromine is in the 4th row. So therefore, it's easier to pull one of bromine's valence electrons away from it than it is fluorine, because it has so many core electrons that are shielding the outer valence electrons from the nucleus. So again, to repeat, fluorine has a higher ionization energy than lithium because it has more protons than lithium, and yet all of its electrons are the same distance away in the 2nd orbital. And fluorine has a higher ionization energy than bromine because its valence electrons are closer to the nucleus, whereas bromine has a lot of shielding electrons in the 1st, 2nd, and 3rd orbitals that are blocking the valence electrons from the nucleus. Okay, electronegativity. It's kind of the same concept in a sense of how much a atom wants to pull in an electron or hold on to an electron, but electronegativity is how much an atom wants to pull an electron towards it. So ionization energy is how much energy it takes to pull an electron away from an atom. Electronegativity is how much an atom wants to pull an electron toward it. The two are kind of similar in that they both have to do with how much the atom pulls on electrons, but a different concept as far as really electronegativity more deals with pulling in outside electrons. So the man represents electronegativity. Electronegativity wants to pull in an electron like that, and so that's what electronegativity would do, is pull in an electron from maybe another atom or one that's just kind of floating around freely. Electronegativity is measured on a scale from 0 to 4 called the Pauling scale. So fluorine, which is in the upper right hand corner, remember it had one of the highest ionization energies, it has the highest electronegativity at 4.0. That's the highest possible. So let's look at the trend. So electronegativity increases as you go up a group and to the right in the periodic table. It's exactly the same as ionization energy. So the atoms in the upper right hand corner of the periodic table, fluorine, oxygen, chlorine, have high electronegativities. They really like to pull in electrons from the outside. Whereas the ones over on the left hand side, all the alkali metals, lithium, sodium, potassium, rubidium, they don't like to pull in outside electrons. They're not very good at pulling in outside electrons. So in other words, the direction, the strong ones are the ones in the upper right, the weaker ones are the ones in the lower left. So you'll hear me refer to that, the non-metals over there on the right side, upper right, as being the strong guys, and the weak guys as being the ones over on the left. And this is the same as ionization energy. So let's look at the trends in electronegativity, and there you see a similar kind of perspective graph, and you notice it looks very much like the one for ionization energy. Electronegativity is greatest in the upper right hand corner of the periodic table where fluorine is. One thing you will notice though, there's the lowest electronegativities, there's the highest electronegativities. The elements on the right side of the periodic table are called noble gases. Noble gases have no electronegativity. We will learn the reason for this. So you notice on that periodic table, you don't see helium, neon, argon, krypton. You don't see the noble gases. Although they have high ionization energies, it's really hard to pull an electron away from them. It takes a lot of energy to do that. They have no desire to pull in additional electrons. because they have no electronegativity. And we're going to talk about why that is in another lesson. So lowest electronegativities and highest electronegativities. And noble gases are not shown because they have no electronegativity. So electronegativities are highest when an electron is closest to the nucleus, has fewer orbitals, and the nucleus has more protons. So it's fairly similar to the reasons for ionization energy. So fluorine or lithium has a lower electronegativity than fluorine because it has the same number of orbitals but fewer protons. So lithium does not pull in electrons as well as fluorine. So again, it doesn't have a lot of protons. Protons are what are going to pull in the electrons because protons are positive and the electrons are negative, but lithium doesn't have very many. It only has 3. Fluorine has a lot of protons, so it's much better at pulling in outside electrons into it. Now, bromine has a lower electronegativity than fluorine because bromine has more orbitals, more core electrons. The valence electrons, or I should actually say the outer electrons outside of the atom, are screened from the nucleus, so it can't pull in electrons as well. It's not really about the valence electrons, it's really about outside electrons that it's trying to pull in. Whereas again, fluorine has it doesn't have as many protons as bromine, but there's very little screening that takes place. So those protons can reach out with their positive charge and grab an electron and pull it in. Atomic radius. Atomic radius is half the distance between the nuclei of 2 bonded atoms. So it's basically like the radius of a circle. You can see that atoms are kind of roughly form a circular shape, or a spherical shape really, in 3 dimensions, and is roughly the distance from the nucleus of an atom to the valence electrons. So atomic radius is important because some chemical properties depend on whether an atom can fit into small spaces. So that's why the size of an atom, its atomic radius, might be significant. That's particularly true with solids, when you're dealing with solids where the atoms have to fit together very tightly. So atomic radius decreases as you go up a group and to the right in the period. So notice it's the opposite of ionization energy and electronegativity. As you go from left to right, it's decreasing, not increasing. And as you go up, it's decreasing and not increasing. So let's talk about the reasons why that would be. Atomic radius are highest when an atom has more orbitals and the nucleus has fewer protons. So lithium has a larger atomic radius than fluorine because it has the same number of orbitals but fewer protons. So lithium doesn't pull its electrons in as well as fluorine. It doesn't pull them as tightly. Now that's kind of counterintuitive. That goes against what you would think. Typical lithium atom has 3 protons. They all have 3 protons, 4 neutrons, and 3 electrons. Whereas a fluorine has 9 protons, 10 neutrons, and 9 electrons. It has a lot more stuff. It has a lot more parts to it, in other words, fluorine does, than lithium. And yet fluorine is smaller. That doesn't seem to make sense. If you keep adding protons, neutrons, and electrons, wouldn't the atom get bigger? And the answer is no. The reason that fluorine is smaller is because those 9 protons, what we said earlier, really pull tightly on all of its electrons, including its valence electrons. They pull them in really tightly. And so it makes fluorine smaller. In fact, it's much smaller than lithium. Lithium is a bigger atom, even though it has fewer protons, neutrons, and electrons than fluorine. So lithium over there. Fluorine in the upper right corner has the smallest radius. So now we'll look at bromine. Bromine, this one's easy, this explanation. Why does bromine have a larger atomic radius? Simple. It has more orbitals that keep expanding out and out and out and out away from the nucleus. So bromine has a larger atomic radius than fluorine because it has 4 orbitals compared to only 2 for fluorine. So it's going to naturally be bigger. The diagrams here don't show it as being bigger, but it would be much bigger because it has orbitals, more orbitals. So that one's easier to understand than the first one. And here's actually a periodic table which shows the relative sizes of the different atoms. So the second period elements show that lithium is much larger than neon. So lithium way over on the left of the second period, you can see is much larger, much larger than neon way over there on the right. And you can see how the atoms in the upper right-hand corner are smaller than the ones in the rest of the periodic table. Again, that's because they pull in on their electrons much harder. That's why they have higher ionization energies and higher electronegativities. They're really good at pulling in electrons, and therefore they pull them in tighter, and it makes a smaller radius for the atom. So this is due to the fact that both lithium and neon have 2 orbitals. However, neon has 10 protons pulling on its second orbital, while lithium has only 3 protons pulling on its second orbital. So let's do a summary of these. As we move to the upper right side of the periodic table, ionization energy and electronegativity increase while atomic radius decreases. So you want to be able to explain those, and I'll have you write some paragraphs on that. So ionization energy increases going to the right, electronegativity increases going to the right. That's because there's more protons over on the right-hand side in those elements that pull more tightly on the electrons, and it makes it easier for that atom to pull in its own electrons, to hold on to its own electrons, and to pull in electrons from the outside. So ionization energy is holding on to its own electrons, electronegativity is pulling electrons in from the outside. Also, because that pull is so much stronger over on the right side, the atomic radius decreases. It gets smaller. It pulls in its electrons tighter to the nucleus. Going up the periodic table, ionization energy increases. That's because you have fewer and fewer orbitals, so the electrons are closer to the nucleus, so it holds on to them better. Electronegativity increases. You have fewer shielding electrons, so the protons can look out into space or to another atom and pull away an electron from either out in space or from another atom as you go higher and higher, because there's fewer orbitals and there's fewer shielding electrons. And finally, the atomic radius decreases for an obvious reason. You have fewer and fewer orbitals, so those circles going around the nucleus, there's fewer and fewer of them, and so the radius is smaller. So you should have these memorized, okay, these trends. Okay, so again, let's go through this. So as you go across a period row, more protons are added to the nucleus. The electrons are pulled in with greater force. This means that the atomic radius becomes smaller as you go to the right. The energy required to pull an electron out, ionization energy, becomes greater. And the ability to pull an electron in from the outside, electronegativity, also becomes greater. As we go down on the periodic table from top to bottom, more orbitals are added. This makes the atomic radius larger. You got more of those concentric circles sticking out from the nucleus. And the outer electrons are farther away from the nucleus. This increased distance makes both the ionization energy and the electronegativity less. So those atoms down towards the bottom more easily give up their electrons. It takes less energy to pull an electron away from the elements down, the atoms down at the bottom of the periodic table. And because they have so many screening electrons or shielding electrons, it's very hard for them to pull in an outside electron. Okay, so let's look at this table. This shows the periodic trend for atomic radius. So each column of dots is a period or row in the periodic table. The yellow dots represent the second row, with the top dot being lithium and the bottom dot being neon. The radius decreases across the period for the reasons we discussed earlier. So that very first dot down there on the left side is either hydrogen or helium, I'm not sure which. But the row, you'll see that there's 8 dots in the yellow row. That's the second row. So lithium is the one up at the top. It has the largest atomic radius. And neon is the one at the bottom of this, and that's has the smallest atomic radius in that row. Then, as you add an orbital and you go over to the red dots, you're adding an orbital to the third row, so that's a third orbital. So all of a sudden the radius gets much bigger again. And that would be That would be potassium. Excuse me. Okay, and so now as you go to the red dots up at the top, that would be sodium. And then you keep going across the periodic table in the third row until you get across to argon at the bottom. And then you add a fourth orbital, and that's the blue set of dots. And you go way up, you jump way up to a larger atomic radius. And you'll notice there's a lot more dots when you get to the fourth row. That's because you're into the transition metals. That's all those elements that are in between that you didn't have in the first three periods. And so that's why you have more dots there. So the radius increase with each row because an orbital is added. The blue, brown, and green columns have 18 dots because there are 18 elements in these rows. So if you look at your periodic table, you'll count 18 elements from left to right in those rows. Okay, we're going to talk about a couple of experimental techniques. We're going to talk about them in more detail later on, but one of the things they like to ask you about is some of these experimental techniques. Some of them are experiments or labs that you can do in the classroom, but some of them aren't. They require very expensive equipment, and you can't do them in a classroom, but at least you can talk about them and understand how they work. So mass spectroscopy is a way of determining the mass of an isotope. So remember, isotopes are the same element, but one of them is heavier than the other because it has more neutrons. The other one is lighter because it has fewer neutrons, but they're the same element. And it works on the principle that a lighter atom can turn faster than a heavier one. So if you look at that car, that motorcycle, and that truck, when they try to turn a corner, the motorcycle, which is small and light, can turn much faster than the truck. So if a truck and a motorcycle turn a corner, the lighter motorcycle will turn quicker than the heavier truck. So lighter isotope atoms curve quicker than heavier ones. So mass spectroscopy is a way of determining the mass of an isotope. So it works like this. First, the isotope atom is ionized so that it has a charge. In order to get an atom or any kind of element to move, any type of atom or particle to move, it has to have a charge on it so that you can move it with a magnetic field. If it has no charge, a magnetic field won't move it. So you ionize it, that is, you either add or remove an electron, it's usually removing one, and that gives it a charge so that you can then move it through a magnetic field. A magnet moves the isotope through the tube. So there's a magnet, so the isotope begins over on the left side, and it moves from left to right there. So a magnetic field moves isotope atoms through the tube. 3, the isotope atom passes through a perpendicular magnetic field. So this perpendicular magnet causes the isotopes to curve. So it's putting a magnetic push on it to get it to move to the downward, in the downward direction there. It's not falling down because of gravity. It's because that magnetic field is turning it. And 4, how much the isotope atom curves determines its mass. A heavier isotope will take longer to curve, just like the truck couldn't turn as fast as a motorcycle. So the heavier isotope would be on the top side of that tube because it can't curve as fast. And you can see that its relative abundance over there on that graph, that bar graph over there, it's actually a histogram, is at 100. Now the number's not important, it's just understanding that it's higher. Heavier is going to be a higher number over there. And the lighter isotope will curve faster, so it'll end up on the bottom of that tube, and that would be the one that's closer over on the left-hand side of that histogram. Now we'll talk about photoelectron spectroscopy. Photoelectron spectroscopy, or PES, is a way to determine the ionization energy or binding energy of an electron. The ionization energy or binding energy is equal to the energy of the photon minus the energy required to make the electron travel a distance. So a photon is a particle of light. We're going to talk about that when we get to quantum physics, which we'll spend about a week on. But a photon, just think of it as an energy packet of light. And that can hit an electron in an atom and cause that electron to either go up to a higher energy level or totally be released from the atom altogether and just fly off into space. So the following formula gives the binding energy or ionization energy. So this is how it would work. So here's electron number 1. You can see that's the valence electron in lithium. I've excluded the neutrons because they're not important to this discussion. Electron number 1 is the valence electron in a lithium atom. So let's assume that a photon with 20 kilojoules of energy strikes that electron. What it's going to do, if that's enough to cause it to be released from the atom, it's going to cause that electron to fly out into space. So let's say that that electron follows that black arrow and it flies out with 15 kilojoules of energy. And just trust me, chemists and physicists know how to measure these things. So the energy of that electron coming out is 15 kilojoules. So that's the kinetic energy required to make the electron number 1 travel that far. Okay, we're not going to do electron number 2 yet, but what does that mean? Well, actually we are going to do electron number 2. So now we're going to do the same thing with electron number 2. After electron number 1 has already flown off into space, we'll do the same thing with electron number 2. We'll hit it with a 20 kilojoule photon, and it makes that electron, because remember that inner electron is held tighter. It's closer to the nucleus. It has less energy, so it's going to take more energy to pull it away from the lithium atom. And so let's say that that electron number 2 flies off with 8 kilojoules of energy. So what we can say for electron number 1, going back to that one, that if you hit it with 20 kilojoules of energy and it flew out of the atom with 15 kilojoules, then there must have been, what happened to those other 5 kilojoules? Well, they must have been the energy that was holding the electron to the atom. So in other words, that would be the ionization energy. So let me say that again. You hit the electron, number 1, with 20 kilojoules of energy. It flies out with 15 kilojoules. So something had to happen to those other 5 kilojoules. They were the energy that was required to pull it away, to actually get it to start moving and pull it away from the atom. And so that would be the ionization energy. That's how much energy it took to pull that electron away. And that's what photoelectron spectroscopy does. It measures ionization energy or binding energy. We tend to almost never use the term binding energy in this class, but ionization energy, it measures that. Okay, let's check out electron number 2. So 5 kilojoules is the ionization binding energy for electron number 1. Now let's do electron number 2. So electron number 1 is gone. So you hit electron number 2 with 20 kilojoules of energy. It flies out with 8 kilojoules of energy. So that's a difference of 12 kilojoules. What happened to those 12 kilojoules? Well, there was 20 minus 8, or 12 kilojoules of energy holding the electron to the atom. So you had to overcome those 12 kilojoules just to get the electron to release from the atom. And then you saw that you had 8 kilojoules. It flew out 8 kilojoules. So the way you knew what the ionization energy was is you put in 20, the electron came out with 8, so the difference between those two has to be how much energy the atom was holding onto the electron with. So 12 kilojoules is the ionization or binding energy of that particular electron. Okay, so there was a lot to cover in this lesson, all right? A lot of terminology. You want to try to learn it as quickly as you can, but remember, you're going to be using these terms every day. You'll get used to them with time. So if they don't all stick right away, that's okay. You just want to do the best you can. It's a little bit longer lesson, but there's a lot of important concepts. You're going to be using terms like ionization energy and electronegativity every day. Not so much atomic radius, but those two you will be using every day. All right, so we'll continue on with our next lesson, and I'll have that up for you very soon. Have a good day.